Not really, it's not enough quizzing for today, but for right now, it's enough to put a little fear into you, that's okay. All right, so where are we? Well, we're talking about the humors, we're talking about the chambers. Humors and chambers. Large posterior cavity, also known, this is why we got to be careful with the chambers, they actually say this, vitreous chamber. Well, we know it as a segment or a cavity, because don't we have chambers in the anterior segment? Yeah, we do. We have an anterior posterior chamber. So when we talk about making it difficult to remember, you got all these chambers, you got segments, and you got cavities, and yeah. I had a cavity the other day, or actually a few years back. All that candy I eat. Dang, I just can't get past it. It's almost like every single week there's some kind of holiday that they put new candy out. Easter, and Halloween, and Valentine's Day. And I'm like, boom. And then of course Safeway just puts it all out after the day after for sale. like 3 bags of candy. Yeah. Okay, so large posterior cavity. It's filled with vitreous humor. Okay? Helps stabilize the shape and support the retina. So what happens if you have a low amount of vitreous humor or you're in a sudden collision? Yeah, pops out. Detached retina. Bless you. Okay, lens. Lens fibers, cells interior of the lens, no nuclei or organelles, filled with crystalline, okay, which provide clarity and focus power to the lens. Now, in today's dissection, which we will be having, super fun, okay, in today's dissection, we will be dissecting eyeballs, and you will, okay, be documenting all the information that you see on the eyeball, all of it. We will be dissecting it, you'll be documenting it, you'll be writing it up. It is a lab, so it's official, it's all good, it's worth points, happy days, yay, okay? Light refraction, bending of light, light refraction, bending of light by cornea and the lens, focal point, specific point of intersection on the retina, focal distance, the distance between the center of the lens and the focal point. So somebody tell me where the primary color focal point is. Go for it, you just said it. Fovea centralis. Fovea centralis. Excellent. Fovea centralis. And what's around the fovea centralis? Lucy. What is around the fovea centralis? So we have the fovea centralis, central point. What is around it? I hear someone what is it? Yeah, macula lutea. Macula lutea. Okay, so focal point. What they're talking about is we take that lens and we focus it right down on that spot, especially if it's colored. Okay, that's where our color acuity is, and that's where most of our cones are found. So here's your focal point. Now keep in mind that we actually, let me take you guys back to biology, and if you're in microbiology or you're going to take microbiology, you're going to hear this. Oil immersion. Has anybody heard that before? Oil immersion. It's one of the lenses on a microscope. Oil immersion. Okay? And what it does is it prevents air from getting in there. So you're literally going through the lens of the microscope, through oil, onto the glass that has the specimen you're looking at. Okay? So how many people have looked at a glass of water with a straw in it, and where the air is, the straw is over here, and where the water is, the straw is clear over here? And that's why they used water to water. Oil to water, anyways. And that's because there's less of a bend. Okay? Less of a bend. When you go into air, it actually bends more. So what are we doing? We're striking the cornea, aqueous humor, the lens, vitreous humor, these are all fluids, and then focal point. So just like oil immersion in microbiology, that's what we're doing. We're preventing distortion of the light. Okay? So, light refraction of the lens, accommodation, shape of the lens changes focus, image on the retina. Okay, astigmatism, condition where light passing through the cornea and lens is not refracted properly, visual image is distorted. Then we do what? Ophthalmologist, and they take and blow some air in our eye. Psst. They say, can you see? And you're like, no. They're like, okay. And they look, and they're like, oh, you have 220 vision. Here's your Coke bottles. You're like, I can see. I mean, things have changed. I mean, think about it. In the 80s, the lenses were like this thick. The kid walked around like this. There was craziness. Now, super thin. It's awesome. Okay? This is just showing you how we accommodate for close vision, for distant vision. Okay? Now, ciliary muscles contract, lens is rounded. So that means we're taking tension off of those ciliary ligaments so that the lens does this, boop, and it bulges. Contracting takes tension off. Relaxing lets it do what? And notice it's flattened out. And that's what happens to the lens. So contracting causes the suspensory ligaments to relax. Causes them to relax. So in turn, what happens is the lens bulges. Okay? Relaxing causes tension to occur. All right? Causes tension to occur and flattens the lens out. So it's good to know what happens to get the lens to do what. So one more time. Close vision, muscles contract, lens relaxes. Distant vision, ciliary muscles relaxed. The lens flattens out. Okay, this is a close-up view of it. So nice fat bulge in the lens. Lens is flattened out. Okay, light refraction of the lens. Image reversal, visual acuity, clarity of vision, normal rating is 20/20. That's normal rating. Normal. And that's because at 20 feet, there's our chart. One, two, well, each one of these is a foot, so, and this one's kind of half, so, but still, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 15, 16, 17, 18, 19, boom, 20. Yeah, they even put a piece of tape here. I just want to check their work. I don't trust other people's work on the floor. Okay, and then I go like this, and then I go like this, and I go, okay, and I'm going to read that one right there. So which one are we reading? At 20. So if you couldn't see that, okay, and then 15. So we'll come back over here, and they'll check each eye. Okay, boom, boom, NP, X, T, Z, F, H. What is that? 15. All right? 15/20 vision, which means at 20 feet, you can see what you would need to see at 15 feet. Which means your vision is what? Good. Yeah, good. 20/20 is normal. Okay? So, and unbelievably, yes, I do have 15/20 vision. I've had it all my life. When I'm tired, I go to 20/20, which is crazy. That's kind of funny, but it's crazy. But yeah, and I do have glasses. Can you guys believe that? I have glasses. I wear glasses. I should wear them in for you guys someday so you can see. Okay, it is kind of weird. I do wear glasses, and what I wear them for is so that my eyes can relax. Because I focus so much, I tire my eyes out. So I have a special pair of glasses that I wear so that my eyes can relax. I'm supposed to actually wear them at night because my eyes really focus hard on images, obviously driving. So it causes my eyes to get tired really quick. So I do have glasses. That's how the chart works. Normal vision at 20 feet. At 20 feet, 20/20 vision. So we're reading line 20 at 20 feet, and that tells us what our vision is. Now, most everybody that has glasses should be able to stand up there with their glasses and nail it without any problems. If you can't, Amina, why don't you hop up there and give us a try? I'm kidding. She's like, no. If you can't, well, guess what? Time to visit the eye doc. All right. Light from a point at the top of the object is focused on the lower retinal surface. Bottom of the object, upper, and then we crisscross. It is reversed and upside down. No, standing on your head will not correct it. Okay? Most people are like, if I stand upside down, will it go the right way? No, it won't. Still does it the same way. Okay? Notice the pickets. They're upside down. Notice the color. They're backwards. It's just how we process it. And they're showing you the same idea that a camera uses. Well, I mean, obviously that's how we got it, was we sampled human beings, made a camera after that. Okay, same thing here. Ametropic, normal vision. Ametropic, normal vision. How about that ametropic? It's normal vision. Normal vision. Ametropic, no. Normal vision. Myopia, myopia, nearsightedness. Myopia, nearsightedness. Myopia. Oh, myopia. It's this place where you go and you kick back on the beach and you just kind of myo. Myopia. Okay. Hyperopia. Now, hyper means excessive. Okay. Notice that it's actually overshooting. It's overshooting. So, corrective lenses will take care of that, yes.
Do they know why people's eyes do this?
Sometimes it's the lens, sometimes it's the shape of the eye. So some people will be born where their eye, instead of being out here where it's supposed to be, actually finishes growing inside. So your lens still does what it's supposed to. Your lens is fine. It's just your eyeball's a little smaller. And so it overshoots it. And the opposite of that, your eyeball's just a little bit bigger than it's supposed to be. Yeah. We can have problems with our lens, failure to contract or relax. Yeah.
So what about like laser eye surgery? What does that do?
It depends on what you have, on what they're using it for, but it is lens corrective surgery. So they actually just make sure that your lens is doing that, lining it up. So it's like anything, if a window's dirty, what do? We clean it. Can we see through it? Yeah. In this case, we're cleaning the lens. We're cleaning it up so that we can actually focus on the object properly. And we were talking about that the other day. It's actually a darn good process. One of my friends just did it, and for about a week and a half, he wasn't supposed to do anything. He had to wear glasses and be all mellow and everything. After that, he's like, I can see everything. So yeah, really good vision. Okay, hyperopia. All right, visual physiology. Visual physiology. Now this is where I'm going to say there's certain things you guys have to know. You have to know everything about it. And then there's other things that I feel that are a little convoluted, so you don't have to know. Okay? So, visual physiology, rods respond to almost any photon regardless of the energy content. Cones have characteristic ranges of sensitivity. Now, we're talking rods. Remember, it's all about dark. It's all about dark. It's all about dark. Now, it's going to take a little bit, but guess what? The people up front are safe from this. The people in the back, unless you turn around and look at the window, are not. Your eyes are going to take some time to adjust. But right now, the biggest majority of it's going to your rods. Your rods are picking up. Now, remember, it's not yes or no. It's yeah, no. You're not just having one rod and one cone work. You actually have them working collectively all the way across the spectrum. So don't think, oh, when it's dark, only my rods are working. No, 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 no. Your cones are working too, just not to the extent that they are because there's a lack of light, color. Okay? As for those good old rods, they're kicking in, they're picking it up. But notice how when the lights are out, don't the colors dull out. Like when you look at other people's colors on their shirts and stuff, they start dulling out. Well, we don't have the light to bring that to us. Okay? Remember, if it's pitch black, if it's completely dark, we don't see anything, but we are sending signals saying we don't see anything. Okay? We are sending signals we don't see anything. That's a good way to find out how you guys react when your parents walk in and flip on the light, right? You're like, oh, no. It's Saturday. All right, so anatomy of rods and cones. Outer segment with membranous discs. Inner segment, narrow stalk, connects outer segment to inner segment. Well, those discs are filled with chemicals. Like everything, it's filled with a chemical, right? Because anything we do in our bodies is chemical. Now, what about the electrical aspect of it? Well, that doesn't come along until what? Transduction. We don't have a nervous impulse until after it's transduced, which means we have to do all these chemicals to get that electrical current we need, right? Now let's go back to the fundamentals of the nervous system. Everybody remember the fundamentals? Let's go back to that, okay? Fundamentals. Let's go back to fundamentals. Susan, fundamentals. Okay? What were the chemicals that caused an electrical reaction on the neuron? On the neuron. So outside the neuron going in, what was that chemical? Yeah, sodium. I know, it's a trick question. Sodium. And what went out? Potassium. Did we start off with chemicals? Did those chemicals help us with the electrical current? Sodium had a positive charge. Potassium had a positive charge. Right? When sodium went in, we became more positive or less negative. Did it create a current? Yes, it did. That's what they're talking about. What we're doing here is we're just starting off with the chemicals. Okay, and this is actually actually a little convoluted, but we're starting off with the chemical aspect of it, because don't we have to generate a graded potential? Yeah, we do. We have to generate a graded potential. Visual pigments is where light absorption occurs, a derivative of rhodopsin. Opsin plus retinol. It's nice that they actually name them after parts of the eye, which helps. Retinol is synthesized from vitamin A. Retinol is not vitamin A. Retinol is synthesized from it. Okay? So we have to process it first, and when we process it, then we pull out retinol. So opsin plus retinol is rhodopsin. So what are they talking about here? Well, we have an outer segment and an inner segment. What you have to know, and you have to dig in deep. Now we're going to talk about some of these chemicals, but you have to dig in super deep. Graded potential. Graded potential. And then an action potential. That's right. Graded action. Graded action. Now, they're giving us a quick overview of what we already know. We know that light comes in, goes up here, strikes the pigmented layer, and then turns right back around and comes into these guys. Now, notice what they're saying. It says, in a cone, the discs are infoldings of plasma membrane. So, in other words, that's what the plasma membrane is doing all the way down. Okay? And the outer segment tapers to a blunt point. Then it says, in the rods, each disc is an independent entity, and the outer segment forms an elongated cylinder. Okay? So, does it look like a cone? Yeah. Does it look like a rod? Yeah. So, how do you think they got their names? Clearly their appearance. Now, we know them as an ice cream cone and a big black hot rod. But they got them from their appearance. Now, let's see what they're saying. It says the outer segment of a photoreceptor contains flattened membranous plates or discs that contain visual pigments. The inner segments contain a photoreceptor's majority organelles, and it's responsible for all the cell's function other than photoreception. It also releases the neurotransmitter. So, if we go back to a neuron, what part of the neuron itself took care of the entire neuron? The soma, yeah, the cell body. Didn't it have a nucleus, a nucleolus, and organelles? It had everything it needed, right? Now, what about the axon? What did that do? Yeah, that was just transmission. It was transmission, that's all it was. They're saying the same thing. This is the chemical aspect of it. Okay? This is the chemical aspect of it. So, this is like a gigantic dendrite. Goes to the cell body, and then down here we release what? Neurotransmitters. And we do the same for the other side. So we end up moving across the cell body, but the cell body is mainly taking care of the cell's functions. So we have this wonderful chemical mixture that generates a graded potential to release or inhibit neurotransmitters. Okay? So this is in each rod a disc. It's independent. There's our retinal. There's our rhodopsin. Okay? Color vision. Integration of information from red, green, and blue cones. Color blindness is the inability to detect certain colors. We all know that, right? It's predominant in men. Men have it more than women. Okay, I've only met a few people, and I actually grilled them. I was like, really? You're colorblind? Tell me about it. And really all they said was in order to pass their test so they could drive their vehicles, that they had to memorize the position of the lights. Because what is a stoplight? Red and yellow and green. The inability to detect certain colors, red and green. Really? Well, it's green. Better know the position. So yeah, they have to know the position of the lights. And now I think about it, I'm like, yeah, what are the positions? Red is, yeah, but where are they? Red's on top or green's on top? Green's on top? Red's on top, then yellow, then green. I know. Are you colorblind? How many red lights have you run? Just curious. Just curious. All right, there's our spectrum right there. No big deal. Nothing, nothing to see here. But notice our rods. They're like, I got this. Everything. Okay, they got everything. But there's our blue, our greens, and our reds, and then rods. What color is the rod? Okay, does everybody see the 15 in this?
12.
What? Aramis, what do you see? And don't say elephants. He's like, I see elephants. Yeah, so you should be able to see the 12. If you cannot see that 12 in there, guess what? Well, you're running red lights. Okay? Well, it's black and white. She's looking. Okay, really? Okay, Louisa, it's your turn. What color? I don't see red. I don't even see a 12. All I see is dots. Black and white, Louisa. Right. I don't see the colors. It's in black and white. Photoreception. Photon strike retinal portion of rhodopsin. Molecule embedded in the membrane of the disc. Opsin is activated. So you know what this is like? This is like a gigantic G protein type situation. Kinda. Okay? Because we actually have to do something to activate it. So opsin's activated, bound retinal molecules, has two possible configurations. Okay? 11 cis or 11 trans. What do they do? Well, that's all we need to know is what do they do. Okay? So photon comes in, 11 cis, and then we become, so the bound retinal molecule has two possible configurations, 11 cis form or 11 trans form. Normally, the molecule is in the curved 11 cis form. On absorbing light, it changes to the more linear 11 trans. This change activates the opsins molecule. That's all that's occurring. So light comes in. Now notice to say normally. There may be some anomalies out there, but normally it comes in, strikes it, and converts it from cis to trans. Yeah. Opsin activates transducins. Wow, didn't we have gusducins? What was that in? Taste. Yeah. Taste, which in turn activates PDE, phosphodiesterase. Transducin is a G protein. So what are we actually processing here? Second messenger, yeah. Okay, a membrane-bound enzyme complex. So then we create something. Now let's just go back to second messenger, what we know about it, and let's just match it up to this. In second messenger, what were some of the things that could occur? So we bind, we start the G protein process, we can do several things at the end. What are the things at the end we can do? We can open a channel, right? We can produce an enzyme, or we can produce a protein. You guys remember that? So we can tell DNA, hey, you know what, we need this protein, or we can produce an enzyme, or we can open a channel. Right? And isn't opening a channel just like direct contact? Like we go, we open the channel, right? So, yeah, so those are the things we can do. In this case, opsin activates transducin. Transducin, in turn, activates PDE. Okay? Cyclic GMP levels decline and the gated sodium channels close. Gated sodium channels close. Okay? PDE is an enzyme that breaks down cyclic GMP. The removal of cyclic GMP from the gated sodium channels results in their inactivation. Okay, so big picture now. Big picture, I want you guys to focus on this for a second. Let me bring this board over. I want you to think about this for a second, okay? Don't look at your books, don't look at anything. What they said is, in the presence of light, this process occurs. In the presence of light, this process occurs. This process, removal of cGMP from the gated sodium channels, results in their inactivation. That means they were active. That means they were releasing something. They were doing something. So in the presence of light, we inactivate the gates. So in the presence of darkness, what do you think we're doing? Activating them. So if light is inactivating them, if there's no light, which is darkness, it is activating them. Okay? The rate of Na entry into the cytoplasm then decreases. Inactivate, decrease, they go hand in hand. Okay? So here we go. Active state in light. Dark current is reduced and the rate of neurotransmitter release declines. So they're saying that in darkness we secrete more neurotransmitter. We secrete more neurotransmitter. So in the presence of light, we reduce the release of neurotransmitter. So it says the reduction in the rate of Na entry reduces the dark current. At the same time, active transport continues to export Na from the cytoplasm. When the sodium channels close, the membrane potential drops towards negative 70. So that means it was open. Now we're going back the other way. So what do you think that neurotransmitter was doing? Do you think it was stimulating or inhibiting? Okay, well, hold on to that thought for a second. We're going to get back to this. Okay? So it drops towards negative 70. Hyperpolarization, the rate of neurotransmitter release decreases. So now we're stopping the release of neurotransmitter. So unbelievably, we're going to start a new process. This is the presence of light. Now I'm going to go over this a couple more times, but I'm going to go over it in a very simplistic manner after we go through this long, convoluted manner. Okay? Then it says, right here it says, this decreases signals the adjacent bipolar cell that the photoreceptor has absorbed a photon. After absorbing a photon, retinal does not spontaneously revert to cis11. Instead, the entire rhodopsin molecule must be broken down into retinal and opsin in a process called bleaching. Okay? So, this is convoluted, it's overwhelming, and I know you guys are thinking, I don't get it. Did I say that we had a graded, and an action? I did. We have a graded, and action. So what we have to do is, in the presence of light, we have to stop an inhibiting neurotransmitter. We have to stop an inhibiting neurotransmitter so that our next graded potential can cause a action potential. If not, it is literally graded, nothing. But if we inhibit it, if we stop the inhibitory neurotransmitter, then the next graded potential can do what? Stimulate to a action potential. Okay, so recovery after stimulation, well, there's the bleaching, and night blindness results from a deficiency of vitamin A. Remember, vitamin A isn't what it is. It has to be synthesized. Okay. This is what I want you guys to focus on, no pun intended. On absorbing light, retinal changes to a more linear shape. This change activates opsin molecule. Opsin activation changes the Na permeability of the outer segment, and this changes the rate of neurotransmitter release, which means we know it slows it down. Okay? Changes in the bipolar cell activity are detected by one or more ganglion cells. The location of the stimulated ganglion cell indicates the specific portion of retina stimulated by the arriving photons. So in other words, let me come over here. What's going on with this? This is inhibiting this. This is inhibiting this. So if we stop this one from inhibiting this one can now do what? Get up to negative 55 to create a action potential in the presence of light. Can you send a signal if there is no light? Well, we're inhibiting it, so no. You can't send anything. Now you can send other signals saying, hey, I can't see light. But no, you can't. So then it says, after absorbing a photon, the rhodopsin molecule begins to break down. Okay, this is known as bleaching. So when that molecule breaks down, it's bleaching. Retinal is converted to its original shape. This conversion requires energy. So now let's just sit here and think about this. When you're staring at stuff and you're processing stuff and you're trying to learn stuff and you're using your eyes all the time, after a while, do you get tired? Why? Because you're using a tremendous amount of energy. It takes energy to process the information that's coming in. You're using a tremendous amount of energy. All right? Once the retinal has been converted, it can recombine with opsin to form rhodopsin, and the process starts again. So literally what's happening is this neuron is inhibiting this neuron. This neuron can now no longer send anything. In the presence of light, we stop this neuron from secreting a neurotransmitter or releasing a neurotransmitter, which is inhibitory. If we stop this one from doing that, what can the bipolar cell do now? It can create a graded potential that will potentially create a action potential, but only in the presence of light. Any questions? Only in the presence of light. Now, all that other stuff's convoluted, but if we say graded action, it makes sense now. Because if this graded potential is secreting an inhibitory neurotransmitter, is this neuron doing anything? No, because we're inhibiting it. So, there's our three neurons. Dark, okay? This is going to inhibit, okay? God, I really wish I could spell. Let's just try this again. Inhibit. Nothing. Okay? So this one is releasing a neurotransmitter that inhibits this one. So can this one do anything now? No. In light, we stop the release. Okay? So this one is excited, and then we go to the brain. So in dark, we release a neurotransmitter that inhibits. Can this one do anything to this one now? No, if you've inhibited this neuron, nothing's going to happen down here. But then in light, this stops the release, excites this neuron then excites this neuron, and we can actually see something. Now that's very simplistic, but that's what they're saying right here. They're taking all these wonderful words, okay? Right? 11 cis, 11 trans, transducin. Okay? They're taking all these wonderful words and they're making this right here. But they're saying in the presence of light. So we convert 11 cis into 11 trans. Okay? We stop the release of this neurotransmitter, which excites this neuron, which happens to be bipolar. This neuron can now release its neurotransmitters to this neuron, which in turn sends a signal to the brain. Any questions? Maria, do you have a question? Any questions at all? Okay, so let's take a closer look. Light and dark adaptation. Dark, most visual pigments are fully receptive to stimulation. In the dark, they're fully ready to take everything on. In the light, pupils constrict, bleaching of visual pigment occurs. So if you have too much light, your eyes are going to say, whoa, too much. They're not going to open up wide, they're actually going to constrict down. Visual pathway, well, begins at the photoreceptor, ends at the visual cortex of the cerebral hemisphere. Message crosses two synapses before it heads towards the brain. Photoreceptor to bipolar cell to ganglion cell. So in light, photoreceptor stops the release of neurotransmitters here. So the bipolar cell can then send a signal to the ganglion cell. The ganglion cell can send a signal to the brain saying, we see light. Now, ganglion cells monitor a specific portion of field of vision. M cells, or ganglion cells that monitor rods, are relatively large, provide information about general form of objects, motion, and shadows in dim light. Everybody take a look around you, because here we go. Now all you're doing is focusing on a silhouette. As before, when the lights were on, you were focusing on colors, definition. Now all you're focusing on is an outline. You're trying to actually get to that point where you can focus on every little thing, but you're focusing on outlines. Literally, when I look out in the classroom, I see this. All the way through the classroom. I'm slowly starting to see where your eyes are. Okay? Slowly starting to pick up more colors. But for the most part, when I first did that, no, it was just